So I think, yeah, one of the reasons we are here today. So everything started in 2012, right? That was in computer vision with ImageNet competition. At that time, so that was huge at that time, but now it's nothing. So we use 1.2 million images. Each image has 224 by 224 pixels. And the architecture that we use was convolutional neural networks. Okay, so that was the old architecture from 1990, I don't remember exactly, so it's a very old architecture. It has 8 layers and 61 million parameters. Okay? The hardware was basically using 2 NVIDIA GPUs. Okay, 1.6 teraflops signal precision. But right away the industry understood that actually it works. Okay, so usually what happens is there is a new technique. We don't know where it works, but it works very well in practice. Okay, and then academia try to understand what's going on. Okay, so we try to publish papers to explain why it works, what is the limitations, and how we can improve. Okay, so this is that was the story basically. But the industry understood very quickly. So they use, for example, at Facebook, they hired Jan LeCun, the creator of CNNs, because they wanted to improve recommendations. Right? They wanted to tag people and then recommend to people, products. So probably the way to make money with deep learning is recommendation. This is the first one. At the same time, there was autonomous vehicles. They say, oh, now we can solve. So if we want to do self-driving cars, we need to solve all the fundamental tasks in computer vision. For example, the depth estimation, mini segmentation. I mean, all these problems are very hard to solve. But with deep learning, now we can solve them. But actually, it was, so we were all very excited, and I say also the same, that in 2 years, in 2000, maybe 14 or 15, we will have self-driving cars. It didn't happen because of the very long-tail distribution of events. So there is this rare events that statistically you never seen before. Okay, so that can be a huge deal. Now it's coming actually. So if you go to Los Angeles, so I was there a few months ago, there are waivers everywhere. Okay, so it's also interesting. Surveillance, so you can use deep learning to monitor a huge number of people in real time. So this was the computer vision revolution. Then 10 years later, so it took 10 years actually to get to the revolution in natural language processing. Okay, so in 2022, so this is GPT 3.5. So the difference is impressive. So the data set is not anymore 1.2 million images. This is actually internet. Okay, so OpenAI scrapped internet. That's what it means. There was 300 billion tokens. So that's a huge number. The architecture, so this is a transformer architecture. It has 100 layers and 175 billion parameters. Okay, so this is where you store internet, right? In this 175 billion parameters. The hardware number of GPUs, from 2 GPUs, 10,000 GPUs. And each GPU has, 15 teraflops of operation. So this is order 10. This is basically what we expect. And the new industry is generative AI. Okay, so this is already used every day. For me, for example, I use that for coding. I'm much more productive, like 30% more productive, using for coding. You can do text summarization, content creation, dialog systems. They are all very, very good. And we have this new name, right? So in machine learning, if we train large network using a large-scale data set, now this is called foundation models. Okay, so it's still a network, but people call it foundation models. So the generative AI, basically this is text generation and image generation, now lately also video generation. So what happened after OpenAI, ChatGPT, Google decided to start closing their research and everything. So now we have basically 2 classes of LLMs. The first class is closed. This is a proprietary LLMs like GPT-4 or GPT-03, Gemini, Claude, and Claude. Okay? But the good news is that for research, I was very worried actually when Google decided to close. The LLM. I said, oh my God, this is the end for research. We just have to pay to get, input and output of this black box LLM. But Meta and Yan LeCun actually forced, to have open source with Llama. Okay, so today there is a discussion if they are still going to, to train open source LLM, but we have Llama. So Llama changed everything for the research community, basically. So we are able to go inside the black box. We can change something. We can fine tune. We can start understanding the reasoning ability of the system. So this is for us very, very important. The dataset that was used for Llama, 15, trillion word tokens. So this is really huge. The architecture, this is very interesting, is that the architecture hasn't changed. It's still a transformer. Okay, so of course we improve a little bit the parts of transformer, like for example the positional encoding. Now this is a rotary positional encoding, which is basically invariant with respect to the translation. The normalization of the layers is a bit different. The activation also a bit different, and then there are different techniques. But basically, this is a transformer. Nothing has changed. So this is very interesting. The hardware now people use 20. So at that time it was 1 year ago 20,000 H100 GPU. If you know the price of H100, you know that this is $4 billion US. Okay, so if you want to train, for example, that was for Llama, for Gemini, for Croc, that was $4 billion. This year they are using 100,000 GPU. So this is 5 times this. That's a huge, that's a huge resource. For image generation, so most models are actually closed. We don't have access to the architecture. So they are like Midjourney, Flux, Stable Diffusion, DALL-E. The open source are Stable Diffusion 2, DALL-E 1, and they are okay but not very good. And the dataset that is used is what is called Lion from Germany, with 5 billion pairs of image and text description. Okay, and you need that both, right? Because when you prompt an image, you are going to use English to generate an image. So you need both, and this is done here. Okay. Architecture, so again, transformer. Okay, so when we get to very large scale, everything is a transformer. All right, so now I go back to the graph structure data. Okay, so the internet is composed actually of all the connections between, for example, if you take the web, there are links between two web pages everywhere. Okay, so when you click, you go to a different page. So basically, this gives you the connections between two web pages. A connection is an edge in a graph, right? Wikipedia, also there are, if you click on this, so this is a graph, right? Wikipedia is a knowledge graph. Internet also is full of JSON file. So JSON file, if you open a JSON file, you will have also links to different parts of the website. So it's pretty clear that internet is a graph, and LLM has been trained on internet, so LLM should have learned what is a graph and how the relationship is encoded. Okay? So of course the question is do we still need GNNs, right? Because GNN is the way that if we know the relationship between data, then we can do better than it would be like a transformer, for example. Okay. So here I'm going to focus on a class of graphs which is called text attributed graphs. Okay, so I'm not going to focus on biology, physics, or chemistry. Okay, this is not my goal. Here I want to focus on text, basically. So the graph that use text is called text attributed graphs. Okay, it is here. So, for example, so the web is an example, knowledge graph is another example. So you have entities, okay, which are the nodes, and then you have the relationships between two nodes. Question and answer, depending on the graph structure. social graphs, Wikipedia, scene graphs as well. So this is examples of text activity graphs. So we call it tags. Okay. So I'm going to use the most popular tag, and I'm going to apply an LLM and see what prediction I have with the LLM compared to a GNN. So the most popular one is called archive. The key characteristic is, so archive is one graph. Okay, this is a social network of articles. The number of articles, the number of nodes is basically 170,000. The number of pages is 1.1 million, and this is a classification task. So each node is an article, and each article belongs to a class of 40 archive topics. So for example, you have artificial intelligence, hardware architecture, data structure, algorithms, and so on. Okay, so this is the archive network. Okay. So the goal is basically given the title, given the title and the abstract of the article, predict the class of this article among 40 possible classes. Okay, that's the goal. So when we use graph neural network, and if we take as a feature the feature given by the database, which is called a GB, which is a bag of word features. Okay, so this is the old technique of, you look at your text, you look at the frequency of some words, this gives you some interactive features, and you have a bag of these features, and you use that, to make prediction. So if we use a graph neural network with this bag of features, we get, 71% accuracy. So the higher the better. The SOTA performance, so it was, when we did that, it was in 2022, is a GNN with a language model, not a large one, just a language model. And these two networks, they are trained simultaneously. Okay, so here the GNN is going to give the relationship, and the language model is going to extract the patterns in the, in the text. Okay. So this was the state of the art in 22, and the performance was around 76.6% precision. What we did is then we paid, at that time everything was closed, so we paid OpenAI. We give the title, we give the abstract, we also provided the 40 classes, and we asked ChatGPT what is the class. Okay. The performance was 72%. Yes?
How do you know that ChatGPT hasn't trained on it?
So, exactly. So, there is a cut-off date when you train an LLM. Okay. And because this data set was already available at the time of the training, there is a very high chance that actually ChatGPT knew about this data set. So even knowing the data set, the performance was not as good as the GNN. So that was for us a good indication. But you're right. So today it doesn't make any sense to use academic benchmark for Gemini, Grok, whatever, because this system has been trained on the internet. So they're already seeing the test set. Okay, so there is a big question today: how do we evaluate the performance of LLMs? How do we compare them? So the golden standard is what we have, which is called Arena, leaderboard Arena. So basically, you prompt something, and then you have two LLMs giving you the answer, but you don't know which LLM they are. And you need to decide between the two LLMs which answer you like most. Okay, you click, and you say, oh, this is Gemini for this. So you do that with a lot of answers from people, and at the end you have what we call an ELO score, like in sports or chess. And this way, this is some kind of the golden standard today to do that. But even that, companies, they find a way also to train an LLM to get the best possible score on this leaderboard. So it's not now the golden score anymore. But this is a big issue. How do we evaluate this LLM now that the data set is usually available on the internet? I think I got a question. Yes?
Yes.
I wanted to ask, did you try a few shots with GPT or?
Maybe please use the microphone.
I wanted to ask if you tried few shots classification scores.
Few shot. No, we didn't. No, for this we didn't do that. No, we didn't try to do that. Yeah, we just do zero shot classification. That's the only thing we do. Yeah. Thank you. Yeah. So I think here that was just for us, an idea. Is it worth continue working on GNN or not? Because if the system was already beating the best GNN, that was the end of the story. Okay. So let's look at the strengths and limitations of both LLMs and GNNs. So we can identify how we can mix the two. So the strengths of LLMs. What we have today is the LLM is basically some kind of oracle, digital oracle. He has seen everything on the internet. He knows everything. And now we have something, we prompt something, right? So there is this movie, Hitchhiker's Guide to the Galaxy, and you go to the oracle, he knows everything about the universe, and then of course the question is, what is the meaning of life? And the answer of the machine is 42. And it's exactly what's going on here. If our prompt is not accurate enough, basically we never get a good answer, right? So we have to find a way to do this prompt engineering, so trying to give enough context, enough information when we prompt the system. Okay. But anyway, so what I was very amazed is actually it produces, he understands the statistics of the language. He's able to not make grammar mistakes or anything, so it's very fluent in English. He has strong zero-shot capabilities through prompting, so you can use that. Today, there is this joke that what is your favorite programming language? It's not Python, it's actually English. Because you prompt, right? And then you use Python. And there is this very interesting scaling laws. So basically the idea is, this is the Xavier Bresson by Richard Sutton. He got the Turing Award this year. So the idea is you put more data, more GPU, you train longer, and your performance, still increasing. So last year, that was true. Okay, we didn't see actually the scaling law getting to saturation. This year, this is not true anymore. So we are getting also to an end very quickly, probably in 1 year, given the race between the big companies. Putting more data, more GPU, the diminishing return is coming very, very soon now. Okay. So the limitations, the most common limitation, for example, if you do healthcare, is going to be hallucinations. Okay, because these systems, they are designed to produce something that looks like truth. Okay, because they maximize the probability. Okay, so hallucination is just part of the design of the system. There is no way we can, with this architecture, solve the hallucination problem. Okay, that's not possible. We need to do something like maybe RAG to improve it, but we will always mitigate and not solve the problem. So they are still, okay, now I should change this line, because yesterday you knew probably that, so for the International Math Olympiad, actually these two LLMs, one from OpenAI, one from Gemini, got the golden middle. So they are getting more and more improved in the sense of logical reasoning. Okay. So for GNN, if you have a graph, this is what I say all the time, GNN is going to shine only if you trust your graph. Okay? Building a graph is very hard. Okay? If you have a natural graph like transportation graph for Google Maps, if you have a natural graph like a molecule, this is where GNN is going to shine, because you really believe your graph structure. And then GNN, what it's going to do, the system is basically reasoning the way it's going to do multiple paths of, a path of multiple hops. Okay? So if the question is the Mona Lisa in the same city as Alice, friend Bob? So this is the Mona Lisa, this is Bob, this is Alice. What the system is going to be trained is basically doing this multiple hops to get to the solution. Okay? A transformer has to learn to do these multiple hops. Okay? So what is a transformer? A transformer is a sequence of token matching. At each layer, you do one token match. Okay? So if you do 100 layers, you can do a sequence of 100 pairwise matching. This is what transformer is doing. Okay? But it needs to learn, the matching. Here, the matching is influenced by the topology of the graph. So if you trust your graph, you're going to go very quickly to the solution. Okay. So this has been, for different modalities. AlphaFold is an edge transformer. So we want to predict the pairwise distance between the amino acids. Limitations, so there is no graph foundation model today in the scale of language and computer vision. Because basically, the community doesn't have enough data sets. Okay, so the biggest data sets are OGB from Stanford, okay? And this is like 40 gigabytes compared to ImageNet, 10 years ago, but more, 15 years ago, 150 gigabytes. So if you want to have a foundation model, you need much more training data points. Okay? The hardware is not optimized. This is what I said yesterday. The sparse linear algebra hardware doesn't exist. So it's very slow compared to dense operations. The last thing, which I think also makes a big limitation, is that industry, so I talk with industry, it's hard for them to understand what they can do with graph. So there is no clear, actually profitable product coming from graph. But in any case, mathematically speaking, we can do graph foundation model, right? Because the graph neural network is independent of the input of the topology. So that can be, a transportation map, that can be a molecule, that can be a knowledge graph. It's completely independent. So you can input to your favorite graph neural network, all these different modalities of graph, and then train your system this way. So this is, mathematically, there is no limitation to learn a graph foundation model. The big limitation are the data set and the GPU. Okay. So today, what we have is basically LLM. If we want to combine LLM and GNNs, the issue is there is a disparity between the quantity of information stored in an LLM and the quantity of information stored in a GNN. Okay? So how do you do multimodal training? So all these systems, Google or OpenAI, they are always trained the same way. So you're going to have a network which is pre-trained for images. You're going to have a network which is pre-trained for text. You're going to have a network which is pre-trained for speech, whatever. And then they make the system multimodal by using some self-attention or cross-attention layers. Okay, so this is how we design the multimodal network. So we have independent network that we train for different modalities, and then we put them together by using some self-attention or cross-attention layer. Okay. If we want to do that with graph, here there is a huge discrepancy between the GNN, which is very small. So the largest GNN is 50 million, and for the LLM, the largest is 500 billion parameters, billion parameters. Okay. So how do you combine these two information is not clear. So what we decided to do, basically we decided to do two applications. The first one is say, okay, so LLM has a lot of information for text. Let's use this information to improve GNN prediction. Okay, that's the first, that was our entry point in this field. And now, which is actually much more interesting, how much time do I don't have much time. The second point, which is more interesting, is that so we know basically they are the big issue of hallucination. Okay, So let's say that we want to ground LLM with Wikipedia. So we ask a question about, I don't know, about the universe, and we want to use knowledge from Wikipedia, and we know this knowledge is trustful. Okay, so the question is, how can we ground the LLM with respect to the Wikipedia information? Okay, so this is a way to mitigate hallucinations. Okay, so this second part is more interesting. Okay, so for the first part, what we did basically is, so this is still the archive. So archive is a social network of articles. The goal is basically to predict the class of each article. So given an abstract and a title, okay, we want to predict what is the class among 40 possible classes of archive. Okay. So what we did is basically we want to leverage the reasoning ability of LLM. So at that time, that was when everything was closed. Okay, we had to pay OpenAI, and what we could only provide is an input text, and then they provided an output text. That's the only thing we could have access. Okay. So we just asked the system, okay, give us a prediction of the class, and also your reasoning. Explain why you decided to do this, this prediction. In the prediction, we asked the top 5. Okay. So the next thing is, when you want to work with GNN, then you need to give not a sequence of words, you need to give a vector, right? Your features has to be a vector. So we need a mechanism to go from sequence to vectors. All right? So to do that, we decided to, so there are 2 ways to do that. The first way would be to use, at that time we have, as an open source, small language model, like BERT, or the BERT, this kind of language model. So what we did is, okay, so we have our article, title and abstract. We prompt, LLM, like GPT 3.5, to get the prediction and the explanation. And then we give that to a small language model, which was the BERT, and we fine-tune this with respect to the solution, okay, to the training set. So we have our, for example, the explanation. It's a sequence of word token, and in the BERT, you know that you have your input tokens, and then you have a class token. Okay, so yeah, that's how it is designed. So you go through L layers of transformer, you get your class token that you fine-tune using an NLP to the correct classes. So this way you are going to have vectors. You are going to represent the sequence of prediction, the sequence of explanation as vectors which are fine-tuned to the task that you want to solve. Okay? So this is the trick here we use basically to go from the output sequence of ChatGPT to a vector given to the GNN. Okay, so that was the only way we could do that in 2022. Then Llama came, and everything changed. So basically now we can have access to open large language model like Llama. There is also Google Gmap, yeah, and of course. I don't remember. The Chinese one. DeepSeek. Yeah, you can also use DeepSeek. Okay. So what you will do basically is that you still prompt your proprietary LLM, which so far is the best LLM. You get the sequence of prediction, of explanation, and then you fine-tune using Llama, for example. Okay. So you will get vectors of very, very expressive this way. And at the end, once you have this, so you have your input vectors for each node, which are enriched with the information from the LLM, and then you train your favorite GNN. Okay, for the task you want. By doing that, so this is the comparison between different techniques. So here, this is the time it needs to be trained. So, so the left, the better, and the y-axis is the accuracy. So the higher, the better. Okay. So if you use a GNN with shallow features like the bag of words, it's going to be very fast to train. Okay, but the accuracy is going to be low. If you use a language model, just use I think it was the Bertha. I don't remember now. The Bertha. So you fine-tune your language model to the task. So no graph, just the language model. So it's going to take some time to train, but it's pretty fast, and the accuracy is better. And then if you train both at the same time, the GNN and the language model, you will get them. Okay, it takes a lot of time to train, and the accuracy is 76. Our model basically is very simple, because you use an LLM which is already trained. You convert into features by fine-tuning using the Bertha, so it's very fast, and then you train your LLM. You see what you have. So this is a good compromise. So there is a leaderboard for the GNN community to compare performance between models on the data set. So for example, archive-AM is the most popular data set. So when we submitted, we get the top performance, and then a bit later, like a month later, there were two other techniques that basically use the same idea. Okay, but with more compute. So from industry, basically it was from industry. Anyway, so of course we got this question I think about the data leakage. Okay, so archive is part of the of internet. So it's possible that this LLM actually has been trained on the test set. So we are cheating in some sense. So what we did is that we still use GPT 3.5. We know the cutoff date. So we decided to construct a new archive in 2023 after the cutoff date of GPT 3.5. Okay, so we are sure that this data set is out of distribution. It's not part of the training set. Okay, and the conclusion is the same. Okay, so there is actually, even if there is leakage, it's not going to change anything. Anyway, so in this first step, that was really when GPT 3.5 came, and we didn't know what to do with that, so we wanted to explore. What we wanted to do is basically extract information from LLM and then give this information to the graph, which has not only the node features coming from the text, but also the relationships between the data. So trying to use the best of the two worlds. Okay. And in the last 15 minutes that I have.
I have a question.
Yes, please.
You said that the archive graph is a directed graph, and yesterday when you were talking about the encoding you were using, there was the eigenvectors from the Laplacian graph, right, from the Laplacian matrix. So, but that is usually not directed. Did you include the directed relationships in that graph for the training or the encoding?
Okay. So you're right. So the Laplacian eigenvectors for the standard application is defined for undirected graph. It is not defined for directed graph. For this, I don't remember what we use for. So one thing, yes, when you have only one graph, you don't need Laplacian eigenvector or the positional encoding. When you have only one graph, because basically you just use the indexing of the node, and it would be enough to have unique identity. Okay, you can use something more elaborated related to the distance, the shortest distance, this kind of stuff. But when you have one graph, you don't compare to anything. So you don't need to have like Laplacian eigenvectors to compare. So yeah, it's to be frank, I don't remember which positional encoding we used at that time. But because there is only one, I'm pretty sure we don't use Laplacian eigenvectors. Yeah. Or if we use it, we don't have any problem with the sign because we have only one graph. So we fix forever the sign, and it's good enough, okay? Because we have a unique identity and the distance between two nodes is related to the shortest path.
There are other ways of using adjacency matrices to describe directed graphs. And you could do a Laplacian on them.
Yes, absolutely.
Okay, then you get complex values and value vectors, and it makes it a little bit more difficult.
I agree.
Do you have any ideas or recommendations for how to use directed graphs in encodings using the Laplacian?
Yeah. So if you have directed graph, we have developed actually a directed transformer that was for a specific application in genomics, where we needed to have some directions. The positional encoding we used was not the Laplacian eigenvector. It was actually coming from the expertise of people from genomics saying, that's actually a better way to have a unique identity for this node in genomics. So this is the part where, when you start working with experts, you ask them, we have this issue of unique identity. We want the network to be able to not be confused because they have the same identity. So can you give us some way to have a unique representation of the node? But we didn't use that. We didn't use the Laplacian for the directed graph. We use expert in this situation. Yeah, that's a very good question. Yeah. Thank you. Again, the Laplacian eigenvector is not the perfect solution far away. Okay, it's just when you don't know what to do. If you have an undirected graph, use the Laplacian eigenvector. If you have a directed graph, you use the random walk positional encoding. So yesterday I introduced that. Maybe we can talk about this during the break. And the random walk positional encoding, so because the random walk is defined on directed graph, it also state of the art for many applications. But again, if you are working on a specific application with experts, ask the experts to help you. That's the best way. Thank you. All right. Okay, so for the last section, I'm going to talk about precisely this issue of how do we mitigate hallucination using a knowledge graph. So something that you trust. Again, you really need to trust your knowledge graph. Okay. So I'm going to introduce. We talk about words, and words are represented by tokens, right? So tokens can be usually subwords. Okay, so for llama, for example, it is trained with I think 35,000 tokens. So all words can be represented by these 35,000 tokens. Okay, so this is called a word token. Okay, for images, a visual token is a patch. Okay, so remember for visual transformer, what they did is you take your image, you cut it into multiple identical patch, and you embed into a vector using MLP, which is shared across the patches, and this is a visual token. Okay. Now I'm going to introduce the concept of graph token. Okay. So today, when we use LLM, it's a bit boring. But they are very good, so we still need to use them. How do we use LLM? So basically, you're going to have your query. Okay, so for example, my query is, what is the name of Justin Bieber brother? Okay, this is a sequence of word tokens. This will go to a text embeddor, so this is the word embedding part, so you get vectors. And then the vectors are going to be given to a series of transformer blocks. Okay, this is the self-attention layers here. Okay. And at the end, the output will produce a sequence which is going to be the answer to your prompt. Okay, so this is your training set. You have a prompt, and then you have the answer, and you train the system this way. Okay. So, even when you are using images, this is going to be the same architecture. The only thing that you're going to change is the input. So instead of being a query, the query is not going to be a sequence of word tokens, it's going to be a sequence of visual tokens. Okay, you take your patch, you embed them in a vector, you have a sequence of vectors, and then you give it to your self-attention layers, and then you produce the answer. Okay? So, you see where I'm going? For graph, it's going to be the same. So for graph, we are going to expand or concatenate the graph tokens to this embedding. This is what we're going to do. We can only work in this stage here. So the first thing we're going to do is that we're going to take the knowledge graph related to this question. What is the name of Justin Bieber's brother? And I'm going to tell you how we get this graph. And we are going to embed this graph using a GNN with a vector, okay? And this vector will be given to the LLM. Okay. This part I'm going to talk about this. Okay. So to embed the graph, and again I didn't tell you how I get this graph. This is the graph file section that I'm going to introduce you. Basically, yeah, I'm going to use my favorite GNN. Okay. So I'm just doing a few layers of graph. Whatever, graph convolution or graph transformer you want, and then you are going to do a mean, and then you are going to apply an NLP on that, and you get one vector. These parameters will be learned during fine-tuning. The second thing is, so remember LLM has a lot of knowledge about graph, but LLM only works with word tokens. So the thing that we decided to do is, we can represent a graph actually with English. And this is how we can access to the knowledge of the graph. Okay? So this is a topological graph, and then the textualization, so we call it this operation textualization of the graph, basically is going to define this graph. So a graph G is a set of directed edges defined by ij, where node I points to node j. The graph G is defined with edges 0, 4, 1, 3, and so on. Okay, so I have actually one-to-one mapping between this topological graph and the textualization with English. Okay. The problem is that there is not only one way to use English to represent the topological graph. Okay, so I call it this is not text equivalent. Okay, there are many ways to represent with English a graph. Okay, and of course, different representation will give you different performance. But still, we need to access to the knowledge of the LLM, and the knowledge is defined by English. Another issue is the scalability. So if you have a Wikipedia, the number of pages is huge, right? 600,000 pages. And the number of edges, the links, the relationship is 200 million. Okay? So this is not something we can append to the question. It's there is a context window for any LLM. So you cannot give Wikipedia as as a prompt. Hallucination, of course. I'm not going to talk more. So what we propose is going to be 4 steps. The first step is going to use GraphPy to retrieve a subgraph from Wikipedia, for example, that is going to be relevant to your query. The second step, we are going to concatenate the user query, the graph encoding token, and the text-based graph tokens as an input to the LLM. Okay? We will generate the response, and then we will train simultaneously the graph neural network, and we will fine-tune the LLM layers. So in this case, that was Llama 2, 7 billion parameters with LoRa. So LoRa is the default technique to fine-tune an LLM today. This is a low-rank fine-tuning. Okay? So instead of, if you have 7 billion parameters, if you use LoRa, you are going to use 0.5% of 7 billions, which is 35 million. Okay, so this is a way you can fine-tune a huge LLM with academic GPU. Okay? And the GNN parameters is 5 million. So the first thing we did is we expanded now the very popular RAG process to graph. Okay? So to do that, it's going to have 4 steps. My first step basically is I'm going to, for example, I have Wikipedia. I'm going to take all the nodes and all the relationships which are represented by text, and I'm going to embed them with vectors. Okay, so I can take, so So at that time, we use BERT. It's going to be frozen. We are not going to do any fine-tuning. And we are going to represent all nodes text and all edge text as a vector. So this is Zn, N is for node, and Ze and E is for edge. Okay, so we store everything in the database. So storing in a vector database today, we have many options. Okay, so it's very fast to do. When you use, when you do Google search, this is exactly what is going now. So your question is transformed into a vector. The vector is, matched to, the database entries, and then you retrieve, the most related documents. So the retrieval is very simple. What we're going to do is that we're going to retrieve the top k most relevant nodes and edges. Okay, so we get a query. What is the name of Justin Bieber's brother? We are going to use the same embedding LLM. So in this case, it was just BERT, a language model, and we get a vector ZQ, Q for query. Okay, and then we just do the dot product. So here the cosine similarity between the query vector and all the node vectors and all the edge vectors, and we retrieve the top k most similar ones. Okay, this is what we do. So we get a graph like this, and this graph is again huge. Okay, so we want to sparsify the graph. So to sparsify the graph, this is a very well-known technique in computer science. So basically what we're going to do is we are going to extract a subgraph which is going to be connected, and there are different ways to do that. So here we use the price collecting Steiner tree because we can have a linear time complexity. So remember that we have the top k information. So this gives us in this situation, some price. So what are the most important nodes and what are the most important edge? If you apply the price collecting Steiner tree, what he will do is that he will extract from a directed graph a sub-directed graph. So starting from a root node, and depending on the weight, so the importance of each node, basically he will extract the most important subgraph. Okay. So this is a maximization problem with respect to a set S of nodes. This is the price coming from the top k retrieve, and this is the cost. Here this is just the number of nodes that you want, and there is a constant that is going to adjust automatically the number of nodes that you want to extract. Okay. We extended a little bit PC ST by considering also the edge information. Okay. So we have our big graph database, and we are able to extract a subgraph from this, which is this one. So once we have the subgraph, we can represent it with text, with English. Okay. So this will be append to the query. Okay. So we have the English tokens. We give it here. Okay. We also give the graph, and basically now we can fine-tune the LLM, and we can also learn the GNN at the same time, given the training set. So we have an input and we have an output. The output is going to be compared with the cross entropy to the ground truth, and then you can backpropagate, and then So this is the technique that we call G-retriever. Basically, first we index, the huge graph. Then we have a query, a question. We retrieve a subgraph. We specify the subgraph, and then we give it to the input of the LLM, and we also project the graph. So here there is a learning linear transformation, which is going to align the graph representation with the English representation. Okay. Yes, please.
That was exactly my question of why do you need both, in the sense of
yes.
why don't you just give the graph representation and skip the text?
Yes.
Altogether?
Yeah. No, absolutely, that's a good question. So, so the two information are complementary. So we did an evaluation study. If you remove the GNN, the performance is going to increase by 22%. If you remove the textualization of the graph, the performance is going to decrease by again 20%. So the two information are complementary. The GNN is able to capture some global information, and the textualization of the graph is able to capture the LLM information. So the two are important, actually. That's an important question. So we are trying to push a little bit in this direction because this is some kind of where we are now with web engines. So web engines started, in '98 with Yahoo, but everything was manually, ranked. So is it good? Is it bad? It was done by humans. This is not something that you can scale up to the internet site. That's not possible. Then there was this PageRank, so basically you compute the largest eigenvector of the random walk matrix. Okay, so that was Google. Then in 2015, they started using Word2Vec, okay, for search. Word2Vec is not dynamic. Okay, it will always give you the same representation whatever the context. It's not as good as Transformer. So then they started using Transformer. So this is Lambda. And then in 2023, at the same time, we introduced RAG with search. And finally now they have Gemini, which is an LLM plus RAG. What we want is basically to promote the idea that, yes, but this is still doing some hallucinations. Now if you have a trustful source of information like Wikipedia, you can decrease very quickly your hallucinations. Yeah, so this is it. So of course you can extend that to multimodal because now, as I said, this is always the same architecture. So you have your visual token, you have your text token, your graph tokens. Everything has the same architecture now. And I think that's it. So thank you very much for coming, for your questions. And of course I take questions.